morning, students. Welcome back to science class on the chapter light. Just recall what we had studied in the previous class. In the previous class, we had studied image formation by convex lens. Okay, so first we kept the object at infinite distance, and we got image at principal focus 2. Okay, first we kept the object at infinite distance. This is convex lens. Okay, so first we kept the object at infinite distance. So we consider two rays parallel to principal axis. Okay, so after diffraction, both the rays are meet at F2 or passes through F2. Okay, so here the position of the object at infinity and position of the image at F2. Size of the image is very small, right? So point size. Okay, size of the image is highly diminished or point size. Then what is the nature of the here? If you keep a screen here, then you will get the image of this object. Suppose if you keep a candle here, then you will get the image of the candle. Okay, so nature of the image is real and inverted. Okay, so next we kept the object at behind C1, behind C1. Okay, behind C1. So here the position of the object is behind C1 and the position of the image between F2 and C2. See, you can take a ray like this also. Okay, you can take ray of point like this also. This ray also meet at this point only. Okay, here. So here just we need two rays. Where the two rays meet at point, at that point, the remaining all the rays meet at that point only. Okay, so to show image formation, we will consider just two rays. Next, so now here position of the object is behind C1 and position of the image is between F2 and C2. Okay, if you place the screen here, you will get the image. Next, what about size? Size it is small, right? So size is diminished. Next, what about nature? So definitely we will get the image. If you place the screen here, okay. So the nature of the image is real and inverted. Okay. Next, we kept object at C1 at the center of curvature. So we keep the object Yes. So now position of the object at C1, then position of the image at C2 only. Okay. Next, what about size? Size is same size. Okay, here object size is equal to image size. Then what is the nature? The nature of the image is real and inverted. Okay. Next, keep the object between C1 and F1. Next, keep the object between C1 and F1. So I keep the object. Okay. So next, conformer passes through optic center. So now position of the object between C1 and F1 and position of the image behind C2. Okay, behind C2 and whatever size. So now size of the image is greater than size of the object. So that's the size of the image is enlarged. Then what is the nature of the image? Nature of the image is clear. We can say that it is a real and inverted. If you place a screen here, you will get the image. Okay. So next we kept the object at F1. Next we kept the object at F1 here. So the rays are parallel to each other. Okay. So position of the image at principal focus 1 and position of the image at infinity. Here the rays are never met, but the rays are very close to each other and they are parallel to each other. Okay. So that's why here also we will get the image. Size is it is highly enlarged. Okay. It is we will get the bigger size. Okay. Then what is the nature of the image? Nature of the image is real and inverted. Next, we kept the object between F1 and O. So now position of the image between F1 and O and position of the image is, so this and that is behind C1. Okay, position of the image or on the same side of the lens as the object. Okay, but see, this case is very important. Why? Because when you keep the object between F1 and optic center, here the image formed by a convex lens is virtual and erect. Here the nature of the image is virtual and erect. Here in this case, here you won't get a real image. Okay, so here because the rays are not parallel to each other and they won't meet. The rays move like this. The rays are diverges like this. Okay, if you increase the distance, then the distance between these two rays keep on increasing. Okay, so that's why when you keep the object between F1 and the optic center, the image formed by a convex lens is virtual and erect. Okay, so position of the object between F1 and O and position of the image is on the same side of the lens as the object, means that is behind C1. Okay, so left side of the convex lens. What about size? Size is it is enlarged. Okay, size is enlarged. See, this is a virtual image. Okay, it's not a real image. Next, what about nature? Nature is virtual and erect. Okay, so today we'll discuss image formation in concave lens. Image formation in concave lens. C1, F1, F2, C2. Okay, so now here also first let's keep the object at infinity. At infinity. consider two rays are parallel to each other. Parallel to principal axis. Concave lens. So now consider two rays are parallel to each other. Okay. Now after refraction, the rays diverges like this. Okay. So yesterday we have studied if the ray of light is parallel to principal axis, how it refracts. Okay. Correct. So now if you see here, now these two rays are they never meet. Okay, so that's why here we won't get a real image. If the rays are meet at one point, then only we will get the real image. So now the rays are diverging. Okay, so here we won't get real image. So now just extend this line in this direction. Okay, see. See now these two refracted rays are virtually meeting at principal focus 1. So here, first one, position of the object, second one, position of the image, third one, size of the image, then nature of the image. Okay. First, position of the object at infinity. At infinity. Then position of the image. See here. Now these two rays are not meeting, but these two rays are virtually meeting at f1. Okay. The position of the image at f1. At f1. Then what is the size of the image? Size of the image is, you can see very small dot, right? So point size are highly diminished. Point size are highly diminished. Then what is the nature of the image? The nature of the image is virtual and erect. Virtual and erect. Okay. Here we won't get real image. Why? Because the refracted rays are not meeting at one point. The rays are diverging. Okay, but these two rays are virtually connecting at M. So that's why here we got virtual and erected image. Okay. So now position of the object at infinity, position of the image at f1, size of the image, point size of illumination, and nature of the image is virtual and erect. Okay. Next. So now keep the object between infinity and optic center. Okay, between infinity and optic center. Between infinity and optic center. Between optic center. So now I will keep the object. See now between here. Okay. So now object is now between infinity and optic center. Consider two rays, one ray is parallel to principal axis. It refracts like this. Okay. One more ray like this. So through optic center. Okay, see here also the rays are not meeting. Okay, so now see if it's like this. See here. Now these two refracted rays are virtually meeting between F1 and O. So which means here we will get the image. Okay. See here position of the object between infinity and optic center. Then position of the image between F1 and O. Between F1 and O. That is optic center. Okay, what about size of the image? Size of the image is diminishing. Size of the image is diminishing. Okay, next, what is the nature of the image? So it's not a real image, right? So nature of the image is virtual and erect. Okay, see here see you can keep the object at C1 or behind C1 or between C1 and F1 here, but you will get the image between F1 and optic center only. Okay, you can keep the object here, wherever. Okay, except infinity. When you keep the object at infinity, you will get the image at F1 principal focus. When you keep the object between optic center and infinity, then you will get the image between F1 and O. Okay, and here the images are formed by a concave lens are always virtual and erect. Here we want to get a real image. Okay. So now just compare convex mirror and concave lens. Okay, convex mirror and concave lens. So first here we kept the object at infinity, right? So here we got the image at principal focus, but here also at principal focus 1. at principal focus 1. Here position of the object at infinity, here also position of the object at infinity. Here the position of the image at the principal focus, and in concurrence the position of the image at the principal focus 1. What about size here? Here size of the image is point sized or highly diminished. Okay, what about here? Here also size of the image is point sized and highly diminished. What about nature? Okay, so already we have studied, right? The images are found where convex mirror are always virtual and direct. So nature of the image is virtual and erect. Then what about the nature of the image in concave lens? Here also nature of the image is virtual and erect. Virtual and erect. Okay. So next. Okay. In the second case, we kept the object between infinity and pole of the mirror. Here also we kept the object between infinity and optic center. Okay. Next. Next, what is the position of the image? Position of the image in convex mirror, that is between pole of the mirror and principal focus, means behind the mirror. Okay. Okay. Next, what about concave lens? Okay, the position of the image in concave lens is between principal focus 1 and optic center. Okay, what about size? Size is diminished, and here also size of the image is diminished. What about nature? Nature of the image is virtual and erect, and here also virtual and erect. Okay. See, now tell me. See, actually, I want to burn a sheet of paper. So, which lens do you use? Whether you use a concave or convex, and where should place that paper? See, when you use a concave lens, here there is a divergence. Okay, but when you use convex lens, then there is a convergence. Okay. So if you want to burn a paper, then you have to keep that paper at f1. Why? Because now sun is at the infinite distance. Okay, the rays are coming from infinite distance. After refraction, all the rays are meet at f2 principal focus. If you keep a paper here, then we can at this point what the heat concentration increases. So then we can burn the paper. Okay, so what are the uses of lenses? We use lenses in telescopes, cameras, and microscope, and etc. Okay. Okay, see here. So now till now we are studied when we keep the object at one point, then we will get the image at some point on the basis of diagrams. So now you had studied in your mirror part. In mirror part, what if you know the object distance and image distance, you can calculate the focal length. Or if you know height of the image and the height of the object, then you can calculate magnification. Or if you know the focal length and image distance, then you can calculate the position of the object. Okay, so here also same. If you know if you know the object distance or image distance or focal length, we can calculate position of the object or position of the image or focal length. For that, we have one formula: 1 by f is equals to 1 by v minus 1 by u. Okay, so this is length formula. Okay, see 1 by f equal to 1 by v plus 1 by u. This is mirror formula and this is length formula. Okay, so here also if you know the position of the image and position of the object, then you can calculate focal length of the lens. Or if you know the focal length and position of the image, then you can calculate position of the image. Sorry, position of the object where the object is placed. Okay, so then here we have studied magnification. Okay, magnification equal to h dash by h. Here also magnification equal to h dash by h. So here we have studied one more formula, that is m equal to minus v by u. Here also m is equals to v by u. Okay, here minus, here m equal to v by u. Here also magnification means just you are comparing the height of the object with the height of the image with respect to height of the object. How many times that image is greater or smaller than the object. Okay, so before moving to problems, just now it is a sign convention in lenses. Okay, sign convention is also same. We'll consider our Cartesian coordinate system. Okay, first we'll study sign convention in convex lens. Okay. So now you have to consider this. This is the origin, right? Here in lenses, you have to consider this optic center as the origin. Okay. Next, suppose I will keep the object here. I will keep the object here. So now this is the distance from, say, the distance between object to optic center is known as image. So object distance. Okay. So now you should write this object distance in negative values. Why? Because see here, this is the origin. Okay, so now you should compare this distance with respect to this minus x-axis. Okay, see in this axis all the values are negative, right? Okay, so that's why, see, not only in lenses, okay, I have to write the object distance in h. Yet height of the object is always positive, then height of object distance always in negative. Okay, see now just take the height of the object. We will compare this height with respect to this positive y-axis, right? Okay, so that's why height of the object we should write in positive, then object distance in negative. Okay, next we will get the image here, right? So now, see here. So this is just imagine I have put an image between F2 and C2. So now, how to write this image? The distance between optic center to the image is known as image distance. We use V to represent image distance. So now, how to write whether we should write in positive or negative? So now we'll compare this distance with respect to this positive x-axis. Sorry, here, right? Okay, so now this distance we will compare with this positive x-axis. Here in this axis, all the values are in positive. Okay, so that's why here we will represent what image distance in positive values. Okay, if you obtain image between f2 and c2, or if you obtain here or here or here. Okay, in this case we'll write the image distance in positive. Suppose if you get the image here, you get the image here. Okay, just this is b. Okay, so in this case we'll write image distance in negative values. Why? Because now we'll compare this distance with respect to x-axis. Okay, next see here, this is our image. Okay, now how to write the height of the image, that is h dash. So now we will compare height of this image with respect to minus y-axis. Why? Because it is below the principal axis side here. So now we should compare the height of the image with respect to this minus y-axis. Here all the values are in negative, right? So that's why we will represent h dash in negative. Suppose this is your, see here, here we obtained image here. Okay, so now in this case, image distance, we'll write the image distance in negative. Then what about h dash? So now we should compare this height with respect to positive y-axis. Okay, so here in this case, we'll write h dash value in positive. Okay, so here we have studied what in convex lenses the real images are found here only, right? At f2, between c2 and f2, at c2, behind c2. Okay, the real images are found this side only. Okay, so clearly we can say that if v is negative, if v is positive, then we can clearly say that the image is real. Okay, because we obtained real images at f2, between f2 and c2, behind c2, and at infinity. Okay, so because see this side all the values are positive, right? Because we should compare these distances with respect to positive x-axis. So that's why if you obtain v values in positive, then clearly we can say that that image is real. Suppose while solving problem, you get answer say v equal to minus 30 or minus 20 centimeter. Okay, minus 20 centimeter. So now see here, if now this is the image. Okay, so now this distance, we will compare this distance with respect to minus y-axis. So now suppose if you obtain v equal to minus 20 centimeter, then clearly we can say that that image is virtual and erect. Okay, so this is a sign convention and focal length. Okay, so now focal length of the convex lens is, we write always positive. Focal length of the convex lens is positive. Okay, next sign convention in concave lens. Okay, so here also same, right? So always we represent in object distance in a negative and height of the image in positive. Okay, see here in a concave lens, always will obtain image at left side of the concave lens, means here only. Okay, so now we should compare this distance with respect to minus x-axis. So clearly we can say that v will write v values in negative. Then what about h dash? Here we won't get real image. Okay, so then what about h dash? So we write h dash in positive. Okay, then focal length of the concave lens is always negative. Okay, this is a sign convention in concave lens. Here, while solving problem, if they mention the lens uses concave, okay, then you should get v value in negative only. Why? Because if you in, see, I am talking in lenses, not in mirror. In mirrors, this is different. In lenses, if you get V values in positive, then the image is real. If you get V values in negative, then the image is virtual. Okay, and we had studied the images are formed by the concave lens are always virtual and erect. Okay, for concave lens, you should get answer for image distance. You should get the values in negative only. Okay, but whatever for convex lens, convex lens sometimes you may get V in positive, you may get V in negative. Why? Because the images are formed by a convex lens are sometimes virtual and sometimes real image. Okay. See here in mirrors, U is always negative. In lenses also, U is always negative. Then height of the image is always positive. Here also height of the image is always positive. Okay. Next, in mirror, if V is negative, if V is negative, then the image is real and inverted. Okay, in mirrors, if image distance, if it is in negative, then the image is real and inverted. Okay, but in lenses, if V is positive, then the image is real and inverted. Suppose here if V is positive in a mirrors, then the image is virtual and erect. But in lenses, if V is negative, then the image is virtual and erect. Okay, see here we'll solve next. Uh, in mirrors, if you get the V values are in negative, then you should get H dash values are also negative. Negative only. Okay. See here while solving problem, if you get V value negative, then you should get H dash value also negative. But in a lenses, if you get V value is in positive, then you should get H dash value in negative only. Okay. But here, if you get V values in positive, then you should get H dash values also positive. But in lenses, if you get V values in negative, then you should get V values in positive. Okay, here both are opposite, but here both are same. Okay, you can cross verify whether you have done that problem correct or wrong. Okay, so now move to problems. A concave lens has focal length of 15 centimeter at what distance at what distance should the object from the lens be placed so that it forms an image at 10 centimeter from the lens. Also, and the magnification produced by the lens. Produced by the lens. Okay. See here, our concave lens has focal length of 15 centimeter. So now here clearly they have mentioned the lens is concave. Okay, focal length of 15 centimeter. So first write focal length equal to minus 15 centimeter. Okay, we'll write the focal length of the concave lens in negative. Okay. Next, at what distance should the object from the lens be placed so that it forms an image at 10 centimeter? It forms an image at 10 centimeter. Okay. So now here we need, see here, at what distance should the object from the lens be placed so that it forms an image at 10 centimeter from the lens. Okay, so here v equal to minus 10 centimeter. Okay, why? Because see here in concave lenses the images are found left side of the lens, so that's why always image distance for concave lens will write in negative. So v equal to minus 10 centimeter from the lens. Also find the magnification produced by the lens. Okay, so first we need u, then magnification. Simple one. You know what is the mirror formula? Sorry, what is the lens formula? That is 1 by f equal to 1 by v minus 1 by u. Okay. So then we can write. So we need v u, right? So better bring 1 by f, 1 by u this side. So that is 1 by f plus 1 by u equal to 1 by v. So now take 1 by f that side. Okay, so 1 by u is equals to 1 by v minus 1 by f. Okay, so no need to write this. First write the formula, then directly write this step. Okay, now substitute the values. 1 by u is equals to 1 by v. So v is minus 10, right? Minus 10, then f value minus 15 centimeter. Okay, next, so 1 by u is equals to minus 1 by 10 minus by minus, that is plus 1 by 15. Okay, then what is the LCM of what is the LCM of 10 and 15? LCM of 10 and 15 is 30, right? Right here. So 1 by u is equals to LCM of 15 and 10 is 30. So now here you have to multiply 3 and here 2. That is minus 3 plus 2. Okay. So here 1 by u equal to minus 1 divided by 30. Okay, because minus 3 plus 2 equal to minus 1. So we need u, right? So finally we can write u equal to minus 30 centimeter. Okay. So now the object is placed 30 centimeter from the concave lens. Next, find out magnification. Magnification. Yeah, we know the formula m equal to h dash by h. But here we can't use this one because we don't know h dash and h. So better go with m equal to v by u. Okay. So what is v value? V value is minus 10 and u value here we got minus 30, right? Minus 30. Okay, so minus will cancel, then magnification equal to m equal to 1 by 3. Okay, here also the magnification it has no unit. Why? Because it is just here we are just comparing how many times the image is greater or smaller than the object. Okay, so here magnification is 1 by 3, that is which is equal to 0.3 or something. So clearly we can say that height of the image is less than the height of the object. Okay, or we can say that the image is one third size of the object. So I will stop here. Tomorrow I will continue the class.